All right, let's now go over a series of simple examples of deriving the asymptotic upper bounds on implemented Java code, the algorithm. Okay, and for each one of them, we definitely got two possible questions for you in the test or in the exam. Either we can ask you to count the precise number of primitive operations, like what we did for the find max method earlier last week. You can definitely review it and do that as an exercise for this example. But what I will try to now do with you will be the second kind of question, which will be we don't really have to be so obsessed about coming up with the precise number of primitive operations. We can simply just approximate about the running time asymptotic upper bound. Remember, whatever, for example, coming up with 4n plus 5 versus 4n plus 6. In that case, asymptotically speaking, you're still going to drop the multiplicative constant and lower term anyway. So they will still end up both being n bigger of n. Right? That's something you want to keep in mind, depending on how you were asked for the question or the problem to solve. But for the next series of 5 problems, we're just going to try to show you how you can approximate the running time for the algorithm. That's what we'll see. Okay, and let me switch to my iPad over here. This one you already stared at, I presume, while you were listening to me. Okay, and for every one of them, I'm just going to give you a chance to pause if you want to, and I really encourage you to really try out every exercise together. All the 5 I'm presenting over here, they are rather straightforward, except for this one formula you have to know, which I will mention when we get to that particular algorithm. All right, so now you can pause the video and think about what the running time is for the first one, which will be finding the maximum between two numbers. Alrighty, assuming that you thought about it, let's now take a look. Okay, so what I will do is I'm still gonna kind of analyze line by line, but I'm not gonna be stressed over about exactly how many primitive operations there might be. You should really know how to calculate the precise number of primitive operations, but it's not the point for this exercise right now. Okay, and for the second one, line number 2 over here, big O of 1, right? It's a constant time operation. Assignments and just assignment and variable access. That's fine, just assignments. And then we got some calculation over here. In that case, that will also be big O of 1, right? It's a relational operation. And also we got another variable assignment over here. So that will also be big O of 1. Okay, and then we got return. That's also big O of 1, right? So what we can do, roughly speaking, you can do is an informal sketch. It's going to be big O of some 1 plus 1 plus 1 plus 1. Well, we know that it just boils down into it would just be big O of 1. That's the ultimate answer. So the family here is just the same as the family here because they can be upper bounded by some constant 1 over here. All right. And another way to think about it is you can think about this part over here is going to be 4, right? That's something I mentioned before, but just let me reiterate. This will be 4, which is equal to 4 times n to the power of 0. N will be input size. However, there's no such n over here in this particular method, but it's just hypothetical. It's kind of imaginary for you to think about. N to the power 0 is 1 anyway. So you're going to drop the multiplicative constant over here, so you only got n to the power 0 being the highest power. That's why it's big O of 1. All right, that's exercise number 1. Hopefully you're okay with that. I think this might be something to remind you what we learned earlier, right? You can see I'm not really too much worried about the precise number of primitive operations, but you should really know how to calculate them if you were asked differently about these exercises. All right, let's now move on. The second one. All right, the second one over here, just to find max over here. You know, it wouldn't be a bad idea to redo this exercise over here, but really from the approximation point of view. All right, you can now pause the video and think about it. Assuming that you thought about it, let's now again go over line by line. This line over here should be a constant time operation, right? Assignments, array indexing, just constant. Right? Constant plus constant will still be constant. So that's big O of 1 over here. What about this part over here? So this part here, you can see this is actually constant over here. It's just single assignments over here Okay, let me just do a bit better over here. And this is more like an upper bounds for the loop counter. So we know that eventually you should really get to very close to n. Very close. But precisely how close, that's something you should know how to calculate from last week. So I would say this is simply big O of n about the header. That's about how many times the header will be executed. It will be some number that can be upper bounded by n. And let's now move on. What about inside the body of the loop? This part over here, the orange one, is going to be, well, comparison, relational comparison, array indexing, all constant over here, right? So that's going to be big O of 1. And this is part of the body of the loop. It's going to be array indexing and also assignments. So that's also big O of 1 over here. And this is also part of the body of the loop. That's I is assigned to I plus 1. Well, also constant. Right? And this is outside the loop about return. So that will be big O of 1. So now how do we calculate? The way to calculate is going to be big O of outside the loop. We got 1. And then we got 1 over here. Okay, I'll just use the color so you can distinguish. And then we got the body of the loop is going to be 1, 1, and 1. So it's going to be 1 plus 1 plus 1. And how many iterations do we have? N iterations. So that'll be n times. And we are trying to aggregate them together. So plus, right? All right, so something like that. Right, let's now try to simplify that. Well, it's I'm pretty sure you already see. Let's just try to be complete. So 2 plus 3n, roughly, approximately. Right? 2 plus 3n. And that's simply just big O of n. And don't worry too much about this 2 plus 3n, not exactly as the precise number of primitive operations. I remember 7n plus 4 or something like that. But remember, ultimately, if you talk about big O, you're going to drop all the lower terms and also multiplicative constant anyway. So they will just end up being in the same family of function. They can both be upper bounded by n. Alright, so that will still be the final answer, the same answer. Right? I think the insight is we are redoing this particular problem over here, but we are now only trying to approximate about the running time rather than calculating the precise number of primitive operation. There are different problems over here. Alright? Alright, next exercise over here. Right? You can take a look at this one over here, but I think the method name tells you about what the intention is for the method. We want to calculate the input array with size n, right? So the n over here is going to be 8 at length. The same convention as the find max that we discussed earlier last week. And the method is simply going to decide whether or not the array A contains any duplicates. So that's why we actually need a nested loop. All right, enough about the hints. All right, you can now pause the video and think about it. All right, assuming that you thought about it, let's now take a look. Okay, and again, our purpose is only to approximate. So start with this line. So this one is about the outer loop, about how many times the body of the outer loop is going to be executed. Well, I know that it's going to start with 0 over here and then get somewhere very close to n. Precisely how close, I don't need to know. Okay, so there's going to be big O of n. And then to help you see that, so I'm going to just highlight this part over here. So this part over here is going to be the body of the outer loop, just blue. Okay, just so that we can know how to multiply eventually. All right, the next one, the next line, line number 3. This will be the header for the inner loop over here, right? What would that be? It's basically just another loop counter over here, j, starting from 0 and get somewhere very close to n. That will also be big O of n, right? Exactly how close, we don't need to know as far as this exercise is concerned. Right, so all I need to do now is to also highlight this part over here. That's the body of the inner loop, right? Over here. Of course, when you're actually solving these problems for test work exam, you may not have the luxury of time to actually color them. But anyway, just for your understanding. All right, so now let's see the body of the inner loop. So it's going to be this part over here. This line over here is constant, right? There's no loop over here, just a relational operator relational operator, logical operator, array indexing, right? Big O of 1. And what about the next line? Well, return statement is going to be big O of 1. And J++, big O of 1, right? Just simple assignments and some arithmetic operation because J is assigned to J plus 1. Big O of 1 over here. And this part here, J++, big O of 1, right? It's part of the outer loop. And outside everything, we also got this, return false. That's big O of 1, right? So now we kind of know about the individual components, but now we need to combine them together and multiplication if necessary. Let's take a look. So what we're going to do is we're going to have a big O over here. And then let's now think about the inner loop. Let's start with the inner to outer. The inner loop is going to be executed for every iteration. It's going to be big O of 1, 1, and also 1. So we somehow got 1 plus 1 plus 1, right? So we got 1 plus 1 plus 1. That's the orange. And then for the inner loop, it's going to be executed for n times, right? And multiplied by that. And also the blue one, don't forget, is also the one over here. That's also part of the body of the loop for the outer loop. So plus 1 over here. And then overall, how many times do we execute the outer loop? Right? It's going to be n multiplied by that. Right? And then outside the outer loop, we also got the purple over here. Okay? Plus 1. All right, so that's basically what we got. Right? Let's now try to simplify that quickly. This part is 3n, apparently. 3n plus 1. 3n plus 1, obviously. And then 3n squared plus 3n. So that will be 3n squared plus n plus 1. Right? If you do the math, simplification, that's what you will get. Okay? That's big O of. In case I make any tiny mistake, definitely correct me, let me know. But the ultimate answer, by dropping the multiplicative constant, also by dropping the lower term, it will be similar. Okay? It will be the same answer. So that will just be big O of. So by dropping the lower term, by dropping the multiplicative constant, that's the only highest power term that we got left. So that will be big O of n squared. All right, let's put it down, n squared. So that's the ultimate answer that we have. Right? Hopefully you're so far comfortable with what the exercises we have gone through. All right. All right, let's now move on to we got 2 more. Okay, the next one. Okay, this one over here. We also got 2 loops. Right? Notice that's really the comparison I want to show to you. Compare exercise number 3 and exercise number 4. For exercise number 3, the 2 loops are somehow nested, meaning that one loop is the body of the iteration for the other loop. On the other hand, this may be a different story. All right. Without further hints, I'll let you pause the video if you want to do the exercise on your own. Assuming that you try, let's now take a look. Okay. Similar convention, we got array input array A and also its size over here. This one here, it can definitely work out exactly what it is supposed to do. The output is not important. We want to be more like a, we want to be make it our second nature. Whenever you're looking at some algorithm over here, if the question only asks you to really derive the running time, you don't really need to know exactly what the algorithm really intends to do. If you can know it at the same time, awesome, brilliant. However, if you cannot, don't worry too much, because your ultimate goal is only to derive the running time. If the question asks you to explain what the algorithm is supposed to do, in that case, of course, you have to understand exactly what the input-output relation is, right? Just be careful. Let's now talk about this line by line, shall we? The first line number 2, big O of 1, right? Assignments, array indexing, nothing complex, big O of 1. And then we got our first loop. This loop over here, starting with 1 or starting with 0, doesn't matter. It gets very close to n, so overall it should be big O of n over here, n plus plus, okay, over here. And here, gotta be careful. because here we actually got plus plus over here, so that means we got increment by 1 every time. But later on, if you actually see something different, you got to consider case by case, right? We might be able to see some further example later. But anyway, just let's focus on this particular one, okay? And then let's now take a look at the body of the loop. This part over here, you can see I just set everything into a single line, right? You can see this part, relational operation, array indexing, assignments, array indexing, just big O of 1. Right, so that's about the first loop. And then outside the loops, we actually got this. This part over here, it's a constant, just assignment. All right, and let's look at the second loop. And for the second loop, over here, it's starting from 0, getting somewhere close to n, and it's just plus plus, incremental. So that'll be asymptotically just big O of n, right? Okay, let's now write it properly. And then let's now talk about the body of the loop. So over here, oh, this one here, itself is actually a nested loop, right? If itself, let me use a different color here. So how about red? And this part over here, what would that be? It's going to be starting from 0, getting somewhere close to n, and also it's incremented by 1 each time. So that will also be big O of n over here. So far we got 3 loops. Don't simply just put n to the power of 3 when you see 3 loops, right? You got to see exactly how the loops are related to each other. And this one is simply one way of relating them. And other problems might got different ways of relating them. Finally, let's now take a look at this line over here, right? Array indexing, arithmetic operation, and also variable assignment plus some arithmetic operation, right? But overall, it's going to be big O of 1. And then finally, let's now put this one here. It's also return outside all the loops, big O of 1. All right, let's now try to put them together. Okay, so what we can get is big O of something over here. Okay, let's say hopefully that's enough space. Okay, let's now start with outside the loop. You got this, you got this. So 1 plus 1 plus, and the first loop. The first loop is actually over here. Let me just try to color that for all of us. This is the first loop. And also, the second loop is actually nested. Let's now put it as well, which is over here. Okay, now it's better. Okay, let's talk about the second one. The second one over here, for each iteration, is going to be big O of 1 for each iteration. And we got n iterations. So it's going to be n multiplied by 1, right, over here. And then we also got this outside the loop constant time operation over here, right? This line over here is also plus 1, right? Outside the loop. It's not part of the iteration. And we are now reaching the final nested loop over here. And outer loop will execute n times. And every iteration for the outer loop is going to be the inner loop, which will be n. And every iteration for n, for the inner loop, is going to be just some constant time operation over here, right? Multiplied by 1. All right, so that will be the final kind of the intermediate calculation you should really know, right? Again, these two parts are really about the two outside the loop constant time operation. This part over here is about the first loop. This part here, also the intermediate outside the loop statements. And this part over here about the nested loop over here, right? You can see the greatest advantage of approximating the running time for algorithm in this way. You can afford to make some minor mistakes as long as it does not change the highest power in your running time formula. That's the insight, right? That's a good thing, okay? On the other hand, if I ask you to really calculate a precise number of primitive operations, in that case, you gotta be precise, okay? Of course, this one here will be a challenging one example. I'll leave that to you, okay? All right, let's now simplify this, which will be big O of, okay, so 1 plus 1, 2, okay, 2 plus n plus, okay, so 2 plus n plus 1 plus n, right? All right, overall, it's going to be 2n plus 3, right? which would be big O of n, right? For sure. That's the final answer. Oh, I beg your pardon. I made a mistake. Beg your pardon. Let me do it again. Of course not. Silly me. Let's now do it again. You can see here, 1 plus 1 will be 2, plus n plus 1 plus n times n will be n squared. Of course, I just missed. Remember I said, as long as you can, as long as you don't really make a mistake on the highest power, it should be okay. But I did make that mistake, which is not good. Okay, plus n squared. All right, so that'll be the ultimate intermediate result. In that case, it will be highest power n squared. So it'll be big O of n squared. Let me write better. N squared. All right, so that's your final answer over here for this second last exercise. Hopefully, so far it's not too bad. I'll definitely bring some more challenging exercises to you, maybe during the Q&A section. So you gotta master the basic first before you can do the more challenging one. Agree?